Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish, just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest. A peaceful space where the day's noise has faded. Wherever you are, you're exactly where you need to be. Tonight we're going to explore one of the most profound and perhaps unanswerable questions humans have ever contemplated. What lies beyond the edge of the universe? We'll discover that this seemingly simple question opens into layers of complexity, revealing how the universe might have no edge at all, or might have edges of different kinds, or might be one of infinite universes in an even larger structure. The answer depends on what we mean by universe and what we mean by edge, but don't worry. This isn't going to be an overwhelming journey through impossible abstractions or a dizzying plunge into logical paradoxes. Instead, we'll move slowly and thoughtfully through the possibilities, building understanding gradually, finding clarity and ambiguity. By the end, I think you'll have a richer appreciation not just for what might lie beyond, but for why the question itself reveals something profound about the nature of existence. If you enjoy these calm explorations of cosmic boundaries and fundamental questions, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in now. Let your shoulders drop. Releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand and release it gently. Feel yourself sinking deeper into comfort with each exhale, and let's begin our slow drift through the question of edges, exploring what it means for something to end and what might exist beyond endings. There's nowhere you need to be, no boundaries you must cross. Just listen, and let the possibilities unfold like space itself, expanding into whatever lies beyond. Before we can explore what lies beyond the edge of the universe, we need to understand what we mean by edge and what we mean by universe, because these terms are more ambiguous than they might initially seem. In everyday experience, edges are familiar. A table has an edge where the surface ends, the ocean has an edge at the shore, your property has an edge at the boundary line. These edges separate what's inside from what's outside. They mark transitions from one thing to another thing. But does the universe have an edge in this sense? Is there a boundary where universe ends and something else begins? The question seems natural, but it immediately encounters problems. If the universe means everything that exists, then by definition there's nothing outside it. An edge would require something beyond the edge to give it meaning. But if the universe contains everything, there's nothing to be beyond. This suggests the question might be logically incoherent, like asking what's north of the North Pole. At the North Pole, the concept of north becomes meaningless. Similarly, at the edge of everything, the concept of beyond might become meaningless. But perhaps we're using universe too broadly. Maybe we should distinguish between different meanings of the word. Cosmologists often distinguish between the observable universe, the region we can observe, and the universe, which might extend far beyond observation. The observable universe definitely has an edge, the particle horizon we explored in previous discussions. Beyond that horizon lies more space we cannot observe. So what lies beyond the observable universe's edge? Presumably more space, more galaxies, more structure, similar to what we see within our observable region. This isn't very mysterious. The edge of the observable universe is just a limitation of observation, not a fundamental boundary of existence. But does the whole universe, including unobservable regions, have an edge? Here the question becomes more interesting and more difficult. If the universe is infinite in extent, stretching forever in all directions, then it has no edge. Infinity, by definition, has no boundary. But if the universe is finite, does it have an edge? Not necessarily. Space could be finite yet unbounded, like the surface of a sphere. On a sphere's surface, you can travel forever without reaching an edge. The The surface is finite in area, but has no boundary where it ends. Three-dimensional space could be similarly curved, finite in volume but without any edge or boundary where it stops. This is one of general relativity's remarkable predictions. Space can have geometry that makes it finite yet unbounded. So one answer to what lies beyond the universe's edge is that there might be no edge at all, just curved space wrapping back on itself. Another interpretation of edge involves the beginning of time rather than space. The Big Bang represents a temporal edge, a boundary in time before which the universe didn't exist. What lies beyond this temporal edge? What came before the Big Bang? These questions parallel asking what's beyond a spatial edge. Some theories suggest time itself began with the Big Bang, making questions about before logically meaningless. Others propose that something existed before, perhaps another universe or a different state of reality. The edge concept also appears in multiverse theories. If our universe is one bubble in a larger multiverse structure, then beyond our universe's edge lies other universes. Are we asking about the edge of a finite but unbounded space? Then the answer is there is no edge, just curvature. Are we asking about the edge of our universe within a multiverse? Then the answer is other universes. It's a question that has occupied philosophers for millennia and now occupies physicists with sophisticated mathematical tools. Yet despite this sophistication, the question retains its primal simplicity. If there's an end to things, what comes after the end? This is the question we'll explore with patience and care, letting each possibility reveal itself gradually. Let's begin with the most concrete edge we can discuss, the boundary of the observable universe at the particle horizon, roughly 46 billion light-years from Earth in all directions. This boundary exists because the universe has finite age and light travels at finite speed. We can only observe regions from which light has had time to reach us since the Big Bang. What lies beyond this observational boundary? The answer is relatively straightforward compared to other interpretations of the question. Space almost certainly continues beyond the observable horizon, with properties similar to what we observe within our cosmic sphere. The CMB, our most distant observation, looks the same in all directions after accounting for local motion. This uniformity suggests we're not near any cosmic boundary. If we were approaching an edge of space, we might expect to see asymmetries, different properties in different directions. But observations show remarkable isotropy. Every direction looks statistically the same, suggesting we're in a typical region, not near any special boundary. Beyond our particle horizon, then, likely lies more of the same, more galaxies, more galaxy clusters, more cosmic web structure, more dark matter, more dark energy. These regions are currently unobservable, but there's no fundamental mystery about what they contain. They're just more universe we can't yet see. As time passes, light from slightly farther regions reaches us, gradually expanding our observable sphere. What was beyond the horizon yesterday might be observable tomorrow. This gradual expansion of the observable universe, as light from more distant regions arrives, is predicted and understood within standard cosmology. They might be radically different. Perhaps physical constants vary at super-horizon scales. Perhaps cosmic properties change beyond observation, but absent evidence for such variation. Assuming similarity is most reasonable, the burden of proof lies on claims of difference, not sameness. The observable universe boundary is thus not an edge of space, but an edge of observation. Space continues. We simply cannot see beyond a certain distance. This makes it the least mysterious type of edge. It's a limitation imposed by finite light speed and finite cosmic age, not a fundamental boundary of existence. In this sense, asking what lies beyond the observable universe is like asking what lies beyond your visual horizon. More of the same landscape, just temporarily hidden. The answer lacks drama but satisfies scientifically. Beyond the observable edge lies unobservable universe, similar to observable universe but beyond reach of electromagnetic signals. This serves as our starting point. The simplest edge has the simplest answer. But as we explore deeper into the question, edges become more subtle and answers less certain. The observable universe boundary teaches us that edges can be observer-dependent rather than fundamental. Different observers at different locations have different observational boundaries. There's no universal edge to observation, only edges relative to particular observers at particular locations and times. This observer dependence of boundaries will recur as we examine other types of edges. What constitutes an edge often depends on perspective and definition. For now, we can say with confidence that beyond the observable universe's edge lies more universe, unobservable but presumably real. This answer, while not mysterious, grounds us in concrete cosmology before we venture into more speculative territory. Beyond the observable universe's edge lies unobservable space. But does this unobservable space extend infinitely, or does space itself have a finite extent? This question asks whether space as a whole has an ultimate edge where it simply ends, or whether it continues forever. If space is infinite, extending without limit in all directions, then obviously there's no edge. The question of what lies beyond becomes meaningless because there is no beyond. Infinity has no boundary by definition. No matter how far you travel, more space remains. There's always farther to go. If space is infinite, it's been infinite since the Big Bang. The Big Bang was not an explosion at a point, but rather a transformation happening everywhere simultaneously. An infinite space can expand. Every region of space grows, increasing distances between points, but the total extent remains infinite. This seems paradoxical. How can something already infinite get larger? But mathematically it's straightforward. Distances grow even though extent was and remains infinite. If space is infinite, then beyond any distance, no matter how large, lies more space. There's no edge to reach, no boundary to contemplate. The question of what lies beyond becomes trivial. More space lies beyond, indefinitely forever. But if space is finite, the question becomes more interesting. Finite space means space has some total volume, measured in cubic light years or whatever units you prefer. Does finite space require an edge? Not necessarily. This is where general relativity's geometric insights become crucial. Space can be finite in extent, yet have no boundary, no edge where it ends. This seems contradictory, but results from space being curved. If space has such topology, then what lies beyond isn't a meaningful question. Space simply curves back, and there is no beyond. Current observations constrain how small such a finite universe could be. If smaller than the observable region, we'd see repeating patterns as light travelled multiple times around. But proving infinity is impossible through observation. We can only constrain how large space must be if finite, never verify infinite extent. The possibility of infinite space is thus always available as an explanation, though not uniquely required by observations. Whether space is infinite or finite but unbounded dramatically affects what lies beyond the edge. If infinite, there's no edge. If finite but unbounded, there's also no edge. Only if space is both finite and flat would there be a true edge, a boundary where space stops. And such an edge would require something beyond. But what could be beyond? If space is everything there is, how can there be anything outside space? This leads to more exotic possibilities. Perhaps beyond our space lies different space, space with different properties or dimensionality. Perhaps our universe is embedded in higher dimensional space. And beyond our three-dimensional space lies more dimensions we don't experience. These possibilities venture into speculative territory, but they illustrate how the question of edges connects to fundamental questions about reality's structure. For now, we can say that observations permit but don't prove infinite space. They also permit finite but large, possibly unbounded space. Both options avoid having a simple edge where space ends. Either space continues forever, or it curves back on itself without boundary. This suggests that what lies beyond the edge might be answered by, there is no edge. at least not in the simple sense of a boundary where space stops. Another interpretation of what lies beyond the universe's edge involves the multiverse concept, where our universe is one of many separate regions in a larger structure. The multiverse idea comes in several varieties, each suggesting different answers to what lies beyond our universe. What lies beyond, in this picture, is infinite variations on cosmic structure, including infinite repetitions of any finite configuration. A more structured multiverse concept comes from eternal inflation theory. Inflation is the hypothesis that the very early universe underwent extremely rapid exponential expansion. In eternal inflation models, inflation never completely ends everywhere. It stops in some regions, creating bubble universes, but continues in other regions. They're separate universes in a meaningful sense, causally disconnected regions where different physics might apply. Eternal inflation predicts not just multiple universes, but infinite universes, continuously being created as inflation proceeds in different regions. What lies beyond our edge is thus an infinite structure of inflating space and bubble universes, with our universe one bubble among infinitely many. Another multiverse version comes from string theory landscape proposals. String theory suggests many possible vacuum states, each corresponding to different physics. If different regions of space settle into different vacuum states, they'd have different physical laws, different particle properties, different constants. The string landscape might contain 10 to the power of 500 or more distinct vacuum states, each defining different possible physics. If inflation populates this landscape randomly, different bubbles would have different physics. What lies beyond our universe is other universes with radically different properties. Most such universes would be inhospitable to life. Physical constants might make atoms impossible, or stars might not form, or chemistry might not work. We observe a universe suitable for our existence not because it's typical, but because we couldn't exist in typical universes. This anthropic selection explains why our universe appears fine-tuned. Beyond our edge lies vastly many universes with different parameters. Quantum mechanics suggests another multiverse interpretation. In the many worlds interpretation, every quantum measurement creates branching realities. Each possible outcome occurs in a different branch. The universe constantly splits into parallel versions containing all possible histories. What lies beyond our universe, in this interpretation, is infinite parallel universes representing all possible quantum outcomes from all events. These parallel universes aren't in different locations, but in different quantum branches, separate but equally real. All these multiverse concepts share a common theme. What lies beyond our universe's edge is more universes, perhaps infinitely many, with varying properties. Whether these other universes are physically real or merely theoretical possibilities remains debated. Evidence for multiverses is indirect at best. Critics argue that unobservable universes don't belong in science, which should focus on observable, testable phenomena. Proponents counter that multiverse predictions follow from well-established theories like inflation and quantum mechanics, making them scientifically legitimate. The debate continues, with no consensus. But multiverse concepts represent serious attempts by physicists to answer what lies beyond. If multiverse theories are correct, the answer to our question is profound. Beyond our universe lies infinitely many others, most radically different from ours. Our universe would be one tiny region in an incomprehensibly vast structure of varied universes, each real, each with its own properties. This expands the answer from beyond lies more space to beyond lies more reality, more existence in forms we can barely imagine. Another type of edge is temporal rather than spatial. The Big Bang represents the beginning of time, a boundary in the past beyond which our universe didn't exist. What lies beyond this temporal edge? What existed before the Big Bang, if anything? These questions parallel asking what's spatially beyond. The standard Big Bang model holds that time itself began with the Big Bang approximately 13.8 billion years ago. Before that moment, there was no time. Asking what came before is like asking what's north of the North Pole. The question becomes meaningless. This answer, while logically satisfying to some, leaves others dissatisfied. It seems to dodge the question rather than answer it. Surely something caused the Big Bang. Surely something existed before, even if not in our current form of time and space. But if time began at the Big Bang, before doesn't exist. There's no earlier moment. Time has a boundary, and nothing lies beyond that temporal boundary. General relativity predicts that classical space-time breaks down at the Big Bang. The equations produce a singularity where density and temperature become infinite. In cyclic cosmology models, this bounce repeats eternally. The universe expands, eventually contracts, bounces, expands again, in infinite cycles. What lies beyond the Big Bang, in this picture, is a previous universe that collapsed and rebounded. Beyond that lies an infinite past of cycles. Before the Big Bang was a higher dimensional space where brains moved. Our four-dimensional space-time resulted from brain dynamics in this larger space. The ekpyrotic scenario, based on string theory, suggests two brains approached each other through extra dimensions. Their collision initiated the Big Bang. What existed before was this higher dimensional structure and the brains moving within it. Our universe is aftermath of brain collision. These models are highly speculative, extensions of incompletely understood theories, but they illustrate attempts to address what came before. Another approach treats time differently. Perhaps time is emergent, arising from more fundamental structures rather than being fundamental itself. If time emerges from deeper physics, asking what came before time began might be ill-posed. The more fundamental description might not involve time at all. In timeless frameworks, the universe simply exists as a mathematical structure. Temporal flow is an illusion or approximation valid only after emergence. What lies beyond time's beginning, in this view, is a timeless reality from which time emerges as an effective description. The heat-death problem also connects to temporal boundaries. If the universe expands forever, eventually it reaches maximum entropy and equilibrium. In this far future heat-death, nothing changes anymore. Time becomes meaningless because no processes occur to mark its passage. What lies beyond this temporal boundary to the future? A static, dead universe where time has effectively ended. Some scenarios avoid heat death through vacuum decay or quantum fluctuations, creating new structures. Time might continue indefinitely with rare events preventing complete equilibrium. But absent new physics, thermodynamics predicts time's effective end in the far future, a temporal boundary at infinity. The temporal edges of the universe, both past and future, thus raise questions parallel to spatial edges. Do boundaries exist? What lies beyond boundaries? For the Big Bang boundary, answers range from nothing exists before, to previous universe phases, to higher dimensional structures, to timelessness. For the heat-death boundary, the answer might be eternal stasis, or quantum resurrections, or new physics we haven't discovered. What we can say is that if time began with the Big Bang before is meaningless. If time didn't begin there, something else existed before. Current physics cannot definitively answer which is correct. We need quantum gravity to penetrate the Big Bang boundary and see beyond. Until then, what lies beyond the temporal edge of the universe remains among the deepest mysteries, perhaps the deepest mystery in all of cosmology. To understand what might lie beyond the universe's edge, we must understand how general relativity describes space, time, and cosmic structure. Since this theory provides our mathematical framework for cosmology. General relativity, Einstein's geometric theory of gravity, treats space and time as a unified four-dimensional space-time that can curve in response to matter and energy. The curvature of space-time determines how objects move. What we perceive as gravity is actually objects following curved paths through curved space-time. For cosmology, Assuming homogeneity and isotropy dramatically simplifies Einstein's equations, yielding specific solutions describing universe-scale structure. The Friedman-Lemaitre-Robertson-Walker metric describes homogeneous, isotropic, expanding universes. This FLRW metric is the foundation of modern cosmology. Within this framework, space can have three possible geometries: flat, positively curved like a sphere, or negatively curved like a saddle. Observations strongly support flat or nearly flat geometry. But small positive curvature allowing closed topology isn't definitively ruled out. In a flat FLRW universe, space extends infinitely in all directions. There's no edge because infinity has no boundary. What lies beyond any distance is more space, indefinitely. The question of beyond becomes trivial in infinite flat space. In a positively curved FLRW universe, space closes back on itself like a three-dimensional analogue of a sphere's surface. This space is finite in volume but has no boundary. Travel far enough in any direction returns you to your starting point. What lies beyond, in closed space, is answered by space curves back. There is no beyond, only curvature returning you to where you started. In a negatively curved FLRW universe, space is infinite, but with hyperbolic geometry. Parallel lines diverge, and space has ever-increasing volume at large distances. Like flat space, negative curvature implies infinite extent and no edge. Beyond any distance lies more negatively curved space. These three geometries exhaust the homogeneous isotropic possibilities. They represent the simplest cosmological solutions to Einstein's equations. More complex solutions exist if we relax homogeneity or isotropy. Anisotropic cosmologies have different expansion rates in different directions. Inhomogeneous cosmologies include structure like superclusters and voids, but on the larger scales, observations support homogeneity and isotropy. General relativity also permits solutions with different topologies, even for the same geometry. Flat space could be infinite or could have periodic boundary conditions, creating a three-torus. These topological possibilities disconnect the geometry question from the finite versus infinite question. Flat geometry doesn't guarantee infinite extent if topology is non-trivial. Einstein's static universe was an early cosmological solution. Einstein modified his equations with a cosmological constant to allow a static, eternal universe. Current observations favour flat or nearly flat FLRW geometry with dark energy. This suggests either infinite flat space or possibly finite but very large space with subtle topology. Either option avoids simple edges. What lies beyond is either more infinite space or curvature returning you to familiar regions. But general relativity might not be the final word. Quantum effects probably become important at very early times and possibly at very large scales. A complete theory of quantum gravity might reveal structure beyond what general relativity describes, potentially changing answers about what lies beyond. For now, general relativity provides our best framework for cosmology. Within this framework, most plausible solutions avoid edges or make edges observer-dependent. The universe described by general relativity is either infinite and edgeless, or finite but closed with no boundary, or structured into multiple regions with boundaries between different domains. Understanding these possibilities requires familiarity with general relativity's geometric language. Space is not a container, but a dynamic structure shaped by its contents. Quantum mechanics introduces different perspectives on what might lie beyond our universe, particularly through interpretations that involve multiple realities. Quantum mechanics describes reality probabilistically. Before measurement, systems exist in superpositions of multiple possible states. Measurement collapses the superposition, producing one definite outcome, but the interpretation of this collapse is controversial. The Copenhagen interpretation treats collapse as fundamental. Measurement physically changes the system from superposition to definite state. But this raises questions. What counts as measurement? Where exactly does classical behaviour emerge from quantum? These questions lack clear answers. The many worlds interpretation offers a radically different view. There is no collapse. All possible outcomes occur in different branches of reality. When a quantum measurement happens, the universe splits. Each outcome occurs in a separate branch. All branches are equally real. In many worlds, what lies beyond our observed universe is infinite parallel universes containing all other possible outcomes of all quantum events. Every time a quantum process occurs with multiple possible outcomes, reality branches. The number of branches grows exponentially with time. If many worlds is correct, this moment is one branch among unimaginably many others. Other branches contain versions of you experiencing different outcomes. Another quantum interpretation, the de Broglie-Bohm pilot wave theory, avoids many worlds while maintaining determinism. In pilot wave theory, particles have definite positions guided by a quantum wave. No collapse occurs and no branching happens. What lies beyond in pilot wave theory is the quantum potential field guiding all particles. This field is non-local, connecting distant regions instantly. The field extends throughout space, possibly infinitely. Beyond any region is more field structure, more quantum guidance. This interpretation is less popular than many worlds, but avoids the extravagance of infinite branches while remaining empirically equivalent. Quantum field theory, the framework combining quantum mechanics with special relativity, describes particles as excitations of underlying fields. These fields permeate all of space. What lies beyond any region is more field, more potential for particle creation and annihilation. The quantum vacuum isn't empty, but seethes with virtual particles constantly appearing and disappearing. Space is fundamentally active at quantum scales. Beyond visible particles and structures lies this quantum froth, the underlying quantum fields that constitute space-time itself. Quantum cosmology attempts to apply quantum mechanics to the universe as a whole, treating the entire cosmos as a quantum system. In quantum cosmology, the universe exists in a superposition of all possible configurations. Our observed universe is one possibility actualized. What lies beyond our universe are the other possible universes in the quantum superposition, all equally part of the total quantum state. The Wheeler-DeWitt equation describes quantum cosmology formally. It's a constraint equation relating different configurations without explicit time. Solving this equation gives the universe's quantum wave function, describing probabilities for different cosmic properties. The interpretation of this wave function remains debated. Do all possibilities exist physically, or does the wave function merely describe our knowledge? If all possibilities exist physically, quantum cosmology implies a multiverse of all quantum-allowed universes. Beyond our universe lies this quantum multiverse, vast beyond comprehension, containing every possible cosmic configuration. The Hartle-Hawking no-boundary proposal treats the Big Bang quantum mechanically. The universe has no initial boundary in imaginary time. Time itself emerges from a timeless quantum state. What lies beyond time's beginning is a quantum geometric structure from which time emerges. This resolves the question of what came before by dissolving the question. In imaginary time, there's no sharp beginning, just smooth geometry. Quantum mechanics thus offers multiple perspectives on what lies beyond. Depending on interpretation, the answer involves parallel worlds, non-local fields, quantum superpositions, or emergent structures. These quantum perspectives complement general relativity's geometric view, together forming a more complete picture of cosmic structure. Ultimately, a final theory of quantum gravity must unify these perspectives, showing how space-time geometry emerges from quantum foundations. What lies beyond might then be understood as the quantum structure underlying classical space-time, the fundamental reality from which our experienced universe emerges. Inflation theory profoundly affects our understanding of what might lie beyond our universe, particularly in its eternal variant which predicts infinite multiverse structure. Inflation was proposed in the 1980s to solve several cosmological puzzles. Why is the universe so flat, so homogeneous, so isotropic? The theory posits that the very early universe underwent extremely rapid exponential expansion, driven by a special quantum field called the inflaton. During inflation's brief moment, space expanded by enormous factors, perhaps 10 to the 30th or more. A tiny region became larger than the current observable universe. This rapid expansion stretched space nearly flat, diluting any initial curvature to undetectable levels. It also stretched quantum fluctuations to cosmic scales. These fluctuations became the seeds for all cosmic structure: galaxies, clusters, the cosmic web. Inflation explains why the observable universe appears so uniform. Distant regions we observe were once close enough to reach thermal equilibrium before inflation separated them. After stretching for a brief period, inflation ended through a process called reheating. The inflaton field's energy converted to ordinary matter and radiation. This reheating created the hot, dense state we call the Big Bang. Inflation preceded and set up the Big Bang phase. In simple inflation models, inflation ends everywhere at roughly the same cosmic time. One brief inflationary period creates one large uniform region. Different bubbles are causally disconnected. Light cannot travel between them because the inflating regions between bubbles expand faster than light. What lies beyond our universe, in eternal inflation, is the eternally inflating space between bubbles, plus infinitely many other bubble universes. The structure is fractal-like. At any moment, some regions are bubbles, some are inflating. The inflating regions create more volume containing more bubbles. The process has no end. Eternal inflation produces infinite bubbles over infinite time. Though each individual bubble has finite age and extent, our universe is one such bubble. Beyond our edge lies inflating space and neighbouring bubbles we can never observe. Different bubbles might have different properties. The inflaton field might decay to different vacuum states in different bubbles. If multiple vacuum states exist, called the landscape of vacua, different bubbles realize different vacua with different physics. Physical constants like the electron mass or the cosmological constant might vary between bubbles. Each bubble has its own effective laws of physics. Most bubbles would be inhospitable to life. Random physics generally doesn't support complex structures or chemistry. We observe a bubble with life-compatible physics, not because it's typical, but because we couldn't exist in typical bubbles. This anthropic selection explains apparent fine-tuning. The physics we observe is constrained by the requirement that observers exist to observe it. Eternal inflation thus naturally produces a multiverse with varying properties. What lies beyond our universe is vast diversity of cosmic conditions. Critics question whether eternal inflation is falsifiable. If other bubbles are unobservable, how can we test the theory? Proponents argue that inflation makes testable predictions about observable universe properties. Eternal inflation follows naturally from inflation if certain reasonable conditions hold. The theory predicts specific patterns in the CMB fluctuations, which have been confirmed. This indirect evidence supports the inflationary framework. Whether inflation is eternal depends on details of the inflaton potential that aren't yet known. Some inflation models are eternal, others aren't. Current observations can't determine which type describes reality. We know inflation happened based on CMB observations, but whether it's eternal remains open. If eternal inflation is correct, it represents the most dramatic answer to what lies beyond. Infinite universes with diverse properties continuously being created. Our universe would be one bubble in an infinite froth of bubble universes, most vastly different from ours, separated by eternally expanding space. The eternally inflating space itself, the region between bubbles, might be considered the ultimate beyond, the background in which universes form. This background is not static, but dynamically expanding, constantly creating more volume, more space for bubbles to form. What exists in the inflating regions between bubbles? Space itself, in a high-energy vacuum state, expanding exponentially. This space doesn't contain galaxies or stars, just the inflaton field in its high-energy state driving expansion. It's the closest thing to primordial void, though not truly empty because the inflaton field permeates it. Eternal inflation, if true, means the universe is vastly larger and more diverse than anything we can observe, with our bubble universe one small part of infinite cosmic structure. String theory, a candidate for fundamental theory of everything, suggests additional structure that might exist beyond our observable universe. String theory posits that fundamental constituents of reality aren't point particles, but tiny one-dimensional strings vibrating in higher dimensional space. Different vibration modes of strings correspond to different particles. The electron, photon, quark, and all other particles are different string vibration patterns. For string theory to work mathematically, space must have more than 3 dimensions. Most versions require 9 or 10 spatial dimensions. We experience only 3 spatial dimensions. Where are the extra dimensions? String theory suggests they're compactified, curled up to microscopic sizes. The string landscape thus provides substrate for multiverse diversity. Beyond our universe lies not just more space, but more possibilities for physics itself. Critics of the landscape argue it makes string theory unfalsifiable. If any physics can occur somewhere in the landscape, how can we test the theory? Proponents counter that landscape predicts statistical properties. By analysing which vacua are common, we might predict typical observable physics. If our physics is typical of habitable vacua, that supports the landscape. If our physics is atypical, it would be problematic. Current analyses suggest our universe's properties are neither extremely typical nor extremely atypical, consistent with landscape predictions. But these analyses are preliminary. The landscape is so vast that exploring it thoroughly remains beyond current capabilities. String theory also suggests another type of beyond. The strings themselves might extend into extra dimensions beyond the compactified ones. If brains, higher dimensional membranes, exist in string theory, our entire observable universe might be confined to one brain. Other brains might exist nearby in the extra dimensions, close in higher dimensional space but inaccessible to us. Particles and forces might be confined to our brain, unable to travel to other brains. Only gravity, which isn't confined, could potentially interact across brains. What lies beyond our universe could then be other brains in nearby higher dimensional space, hosting their own physics and structures. Brain collisions might create universes. The ekprotic scenario proposes our Big Bang resulted from 2 brains colliding in higher dimensional space. Before the Big Bang in this picture was a different state where brains existed separately. Our universe formed from their collision and continues evolving on one brain. What lies beyond might be the higher dimensional space containing multiple brains, only one of which we inhabit. String theory's mathematical sophistication allows entertaining these exotic possibilities. Whether they describe reality remains unknown. String theory has no experimental confirmation yet. Despite decades of work, no unique testable predictions have emerged. The theory might be correct, or it might be mathematical beauty without physical realization. We simply don't know yet. If string theory is correct, it dramatically expands what could lie beyond our universe. The landscape provides diverse physics across bubble universes. Brains provide parallel but separate spaces in higher dimensions. Compactified dimensions provide hidden structure at every point. String theory thus suggests that what lies beyond is vastly richer than visible universe suggests, with multiple layers of hidden structure and parallel realities. But until experimental evidence emerges, these remain theoretical possibilities rather than established facts about reality. For now, string theory provides compelling speculative framework for thinking about what might lie beyond, even if confirmation remains elusive. Beyond mainstream theories like inflation and string theory, various alternative proposals offer different perspectives on what might lie beyond our universe. Loop quantum gravity, a rival approach to quantum gravity, treats space-time itself as quantized. Space isn't continuous but comes in discrete units. At the Planck scale, about 10 to the minus 35 meters, space forms a granular structure. Below this scale, classical space-time notions break down. In loop quantum gravity, the Big Bang singularity might be resolved through quantum effects. The universe could bounce from a previous contracting phase. What lies beyond the Big Bang in this view is a previous universe that collapsed to Planck density, then rebounded. Loop quantum gravity suggests space-time might have discrete structure at smaller scales. What lies beyond our smooth space-time is granular quantum geometry. Causal dynamical triangulations is another quantum gravity approach. It builds space-time from simple geometric building blocks assembled randomly. Through computer simulations, researchers find that classical space-time emerges from quantum fluctuations at large scales. What lies beyond visible space-time might be the discrete quantum structures from which continuous space-time emerges. Conformal cyclic cosmology, proposed by Roger Penrose, suggests the universe undergoes infinite cycles of expansion. Each cycle, or aeon, begins with a Big Bang and ends with heat death. But Penrose argues these end and beginning states are mathematically identical. The infinitely dilute end of one aeon becomes the dense beginning of the next through conformal transformation. What lies beyond our aeon is previous and future aeons. This requires physics we don't yet understand, particularly what happens to black holes in the far future. Penrose proposes they eventually evaporate completely. Once all matter has either left our cosmic horizon or evaporated into radiation, the universe enters a state where scale becomes meaningless. This scale invariant state can be mapped to a new Big Bang, starting the next eon. The process repeats eternally with no beginning or end. What lies beyond our universe temporally, in conformal cyclic cosmology, is infinite sequence of aeons, each an entire cosmic history. Evidence for this might exist in the CMB as circular patterns from black hole collisions in the previous aeon. Penrose claims to see such patterns, though other researchers dispute this. The holographic principle, emerging from black hole thermodynamics and string theory, suggests radical reconception of space. Information content of any region of space scales with the region's surface area. Not volume. This is unexpected and suggests space is fundamentally two-dimensional. Three-dimensional space might be a holographic projection of information encoded on a two-dimensional boundary surface. What lies beyond our three-dimensional experience might be lower-dimensional information structure projecting our reality. The ADS-CFT correspondence in string theory demonstrates holographic principle explicitly. A gravity theory in anti-de Sitter space is equivalent to a quantum field theory. On the boundary, what lies beyond ADS space in this correspondence is the boundary where equivalent description exists. Physics has dual descriptions in different dimensions. Some researchers speculate our universe might be holographic. Perhaps a lower dimensional theory on a boundary fully describes our three-dimensional reality. What lies beyond three-dimensional space might be two-dimensional information structure that generates our spatial experience. Emergent space-time proposals suggest space and time aren't fundamental, but emerge from more basic structures. Perhaps the fundamental reality is quantum information or entanglement structure, and space-time emerges from how this information is organized. In this view, what lies beyond space-time is the more fundamental quantum information network from which space-time emerges. Black hole complementarity and the firewall paradox suggest even our notion of interior and exterior might be observer-dependent. What lies beyond a black hole horizon might depend on whether you're falling in or staying outside. Different observers see fundamentally different realities. This suggests that what lies beyond depends on perspective. There might not be a unique answer, but different answers for different observers. Digital physics proposes the universe is fundamentally computational. Reality might be a simulation running on some substrate. What lies beyond our universe, in this view, is the computational substrate implementing physical laws and simulating particles. This is highly speculative and unfalsifiable, but it illustrates how radically different answers are possible, depending on foundational assumptions. Some philosophers argue the question is ultimately meaningless. If universe means all that exists, beyond the universe is a contradiction. The question presupposes universe is thing within larger context. But if universe is everything, there's no context, no beyond. These semantic arguments don't eliminate curiosity, but they remind us that language and concepts developed for everyday experience might not apply at cosmic boundaries. Alternative theories and proposals thus provide diverse perspectives on what might lie beyond. Bouncing cosmologies suggest previous universes. Quantum gravity approaches suggest granular or emergent structures. Holographic principles suggest lower dimensional descriptions. Digital physics suggests computational substrates. No consensus exists. These alternatives remain speculative, awaiting theoretical development and eventual observational tests. What they share is willingness to question assumptions. Perhaps space, time, dimensions, even existence itself don't mean what we think at cosmic boundaries. The alternatives remind us that our current theories might be approximations valid within experience regimes, but breaking down at extremes. What lies beyond might require concepts we haven't yet developed, mathematics we haven't yet invented, observations we haven't yet made. The history of physics shows that revolutionary insights often overturn confident assumptions. We should expect future surprises regarding cosmic boundaries. For now, alternative approaches enrich our thinking, preventing complacency and encouraging continued exploration of possibilities. When asking what lies beyond the universe, we often imagine nothing might be the answer. But what does nothing mean? And can nothing actually exist? In everyday language, nothing means the absence of things. An empty room contains nothing, meaning no objects, though it still contains air, space, and quantum fields. Absolute nothing would mean no objects, no space, no time, no energy, no physical laws, no mathematical structures. Complete absence of everything. Can such absolute nothing exist? Philosophically, the question is whether absence is a state that can be, or whether existence is necessary and nothing is impossible. If nothing could exist, why does something exist instead? Why is there anything rather than nothing? This is sometimes called the fundamental question of philosophy. Various answers have been proposed across history. Religious traditions often invoke a creator who exists necessarily and creates everything else. But this shifts the question. Why does the creator exist rather than nothing? Positing God doesn't eliminate the puzzle of existence, but quantum mechanics might not be fundamental. It might emerge from deeper structures. Then those deeper structures would exist even in apparent nothing. The question recurses. Whatever is fundamental exists in what we call nothing. So nothing always contains something. Another perspective comes from the mathematical universe hypothesis. Perhaps all mathematically consistent structures exist physically. In this view, existence is automatic for any consistent mathematical structure. Our universe exists because it's mathematically possible. Nothing doesn't exist because nothing isn't a mathematical structure. Only somethings, structures with properties, can exist. This dissolves the question why something rather than nothing by making nothing impossible. Existence is necessary for anything describable. Lawrence Krauss argued that quantum fields and gravity can produce universe from nothing. The total energy of the universe might be zero, with positive mass energy balanced by negative gravitational energy. If total energy is zero, the universe can arise as a quantum fluctuation without violating energy conservation. But critics note this still requires quantum fields and space-time to fluctuate in. It's not creation from absolute nothing. The very concept of absolute nothing might be incoherent. To conceive of nothing requires thinking about it, which makes it something. Nothing, if truly nothing, cannot be described, cannot be thought about, cannot exist even as concept. Maybe the question what lies beyond the universe has no answer if beyond means in nothing. Maybe nothing is impossible and always something exists. Different religious and philosophical traditions treat nothing differently. Buddhism emphasizes emptiness but clarifies it doesn't mean non-existence. Emptiness in Buddhism means lack of independent existence. Things exist interdependently, not as isolated absolute entities. This philosophical nothing differs from physical nothing. It's a different question about the nature of existence. Christian theology developed ex nihilo creation, creation from nothing. But theological nothing differs from physical nothing. It means creation without pre-existing material, not creation in absolute absence of God. God always existed in theological framework. The question of nothing thus depends on framework. Physical nothing, mathematical nothing, theological nothing, philosophical nothing all differ. For our question of what lies beyond the universe, if answer is nothing, we must specify which kind of nothing. Is it empty space nothing, with quantum fields and vacuum energy? Is it mathematical nothing, absence of structure? Is it theological nothing, absence of creation? Each answer means something different and has different implications. Perhaps the most honest answer is that we don't know what nothing means absolutely, and therefore can't confidently say whether nothing could lie beyond. What we can say is that every level of nothing we understand still contains structure. Absolute nothing remains elusive and possibly incoherent. This suggests that beyond the universe, if beyond exists, probably isn't nothing but rather something, though something perhaps radically different from our universe. The question transforms from what lies beyond to what kind of something lies beyond, which is more answerable even if still speculative. A meta-question worth considering is whether the question of what lies beyond the universe can ever be answered, or whether it lies forever beyond empirical investigation. Science succeeds by testing theories through observation. Predictions are compared to experiments, confirming or refuting theories. But regions beyond our universe, by definition, can't be observed. They're causally disconnected, preventing any signal from reaching us. If observation is impossible, can the question be answered scientifically? Or does it become purely philosophical speculation? Other universes might be impossible to observe in principle if causally disconnected. No technology could ever detect them. Does this difference matter for scientific status? Philosophers debate this without consensus. Proponents of multiverses argue that theories predicting them are scientifically legitimate if the theories themselves make testable predictions. Inflation theory makes testable predictions about CMB fluctuations. If inflation is correct and predicts eternal inflation, then multiverses follow. We test the theory indirectly. If the testable parts work, we provisionally accept untestable implications as likely true. This is standard scientific reasoning. We accept atoms though we can't see them, because atomic theory explains vast observations. Similarly, we might accept other universes though we can't observe them, because theories explaining our universe predict them. Critics respond that multiverse predictions are too flexible. Almost any observation could be accommodated in a sufficiently large multiverse. If anything can be explained by some universe existing somewhere, the theory loses predictive power and becomes unfalsifiable. Proponents counter that properly formulated multiverse theories make statistical predictions. Some observations would be more likely than others. If observations match likely predictions, it supports the theory. If observations are extremely unlikely, it challenges the theory. The debate continues without resolution. The scientific status of multiverse theories remains contested. For our question, this meta-debate matters. If the question can't be answered scientifically, what kind of answer are we seeking? Is it mathematical, showing what's logically possible? Is it philosophical, exploring conceptual implications? Is it aesthetic, finding satisfying narratives? Each type of answer has value but differs in nature. Mathematical possibility doesn't guarantee physical reality. Logical consistency doesn't ensure existence. Something can be conceivable without being actual. Yet ruling out impossibilities has value. If we can show certain configurations are logically impossible or inconsistent with known physics, we've learned something. Similarly, showing certain configurations follow inevitably from well-tested theories gives them credibility even without direct observation. The question might be answerable in limited ways. We might not determine exactly what lies beyond, but narrow possibilities considerably. We might distinguish between scenarios consistent versus inconsistent with fundamental principles, between probable and improbable, given current understanding. This partial answering has value. It's better than complete ignorance, even if falling short of certainty. Another consideration is future knowledge. What's unobservable today might become observable tomorrow with new technologies or theoretical insights. The cosmic microwave background was unobservable until predicted and then detected. Many once theoretical entities became observable. Perhaps aspects of what lies beyond will become observable through indirect signatures or unexpected methods. The question's answerability might be provisional. It's currently difficult, but not necessarily permanently impossible. Historical examples show that humans often underestimate future capabilities. Things considered forever unknowable became known. This suggests humility about declaring questions unanswerable. Our limitations are temporary even if some limitations are permanent. Distinguishing temporary from permanent limits is itself difficult. We can't know in advance which is which. For what lies beyond the universe, the answer's nature depends on interpretation. If beyond means spatially beyond observable region, it might eventually become observable. If beyond means outside causally connected regions, it's probably permanently unobservable, but might be inferred from theory. If beyond means logically outside all existence, the question might be incoherent and unanswerable by definition. The question's answerability thus depends on precise formulation. Some versions are answerable, others not, still others meaningless. Clarifying the question is essential before deciding whether it can be answered and what answer would look like. This meta-analysis doesn't provide answers but helps frame inquiry properly. Not all questions admit answers, but some do when properly formulated. The challenge is formulating questions precisely enough to be answerable, while retaining the spirit of original curiosity. The anthropic principle provides one framework for thinking about what lies beyond our universe, particularly in multiverse contexts. The weak anthropic principle is almost tautological. It states that we observe conditions compatible with our existence, because incompatible conditions wouldn't have observers. This is obvious, but sometimes useful. It explains why we find ourselves in habitable universe, without requiring habitable universes to be typical. If a multiverse contains many universes with varying properties, we necessarily find ourselves in one where our type of life can exist. The weak anthropic principle doesn't predict which habitable universe, but it explains why we're in a habitable one at all. For questions about what lies beyond, weak anthropic reasoning helps understand our observation selection bias. We see a universe with certain properties because those properties permit observation. Beyond might contain universes with different properties we can't observe because we can't exist there. The strong anthropic principle makes a more controversial claim. It suggests the universe must have properties allowing observers because observers' existence is necessary. Various interpretations of strong anthropic principle exist, from physical requirements to theological implications about cosmic purpose. The anthropic principle becomes useful in multiverse contexts. If many universes exist with varying properties, most are inhospitable to life. Physical constants have narrow ranges permitting atoms, chemistry, and complex structures. Vary constants slightly, and life becomes impossible. This fine-tuning seems remarkable. Why do our constants fall in the narrow life-permitting range? Religious thinkers cite this as evidence for design. An intelligent creator tuned constants to permit life. But anthropic reasoning provides naturalistic alternative. If a multiverse contains universes with all possible constants, we necessarily find ourselves where constants permit us. No fine-tuning by a designer is needed. We observe life-compatible constants because we couldn't observe incompatible ones. This anthropic explanation only works if a multiverse exists. Without many universes, fine-tuning remains surprising and potentially requiring explanation. Whether a multiverse exists thus matters for whether anthropic reasoning successfully explains fine-tuning. Critics argue anthropic reasoning is unscientific. It doesn't predict specific values, only constrains them to permit observers. Almost any observed values could be anthropically explained in sufficiently large multiverse. The explanation becomes too flexible. Proponents counter that anthropic reasoning makes testable predictions. Constants should be typical among life-permitting values, not finely tuned beyond necessity. If we observe constants finely tuned far beyond what life requires, it would challenge anthropic explanation and suggest design. Current observations appear roughly consistent with anthropic predictions. Constants allow life without being excessively optimized. But debates continue about how to do anthropic probability calculations properly. What counts as typical? How do we weight different universes? These technical debates affect whether anthropic principle has genuine predictive power or merely accommodates any observation. For understanding what lies beyond, anthropic reasoning suggests diversity. If universes vary in properties, beyond our universe lies vast range of alternatives. Most are inhospitable. We're in a rare habitable bubble in a vast sea of uninhabitable universes. This provides perspective on our cosmic significance. Our universe isn't typical or special, except in the anthropic sense of permitting observation. What lies beyond is mostly inhospitable reality, with sparse islands of habitability like ours scattered throughout vastness. The anthropic principle thus connects to multiverse theories. It explains why our universe seems special without requiring it to be objectively special. We're special to ourselves because we exist here, but beyond our universe lies greater reality, where we're just one possibility among many. This humbles cosmic status while explaining apparent fine-tuning naturalistically. Whether this explanation is ultimately satisfying depends on philosophical perspective. Some find it elegant, others find it evasive. It doesn't explain why multiverse exists, or why it has structure permitting some habitable universes. It pushes questions up one level, but it does provide framework for thinking about what lies beyond in a multiverse context, and for understanding our observation's selection effects. Max Tegmark's mathematical universe hypothesis proposes a radical answer to what lies beyond our universe. All mathematically consistent structures exist physically. The hypothesis starts from observation that physics is written in mathematics. Physical laws are mathematical equations describing relationships. Why does mathematics describe reality so effectively? Eugene Wigner called this quote zero in physics. One answer is that reality is mathematics. Physical existence means mathematical existence. To exist is to be part of a mathematical structure. If this is correct, then all mathematical structures exist somewhere. Our universe is one structure among infinitely many. What lies beyond our universe is all other possible mathematical structures, each as real as ours. These include structures with different dimensions, different symmetries, different physical laws, different logical rules. Any structure that can be consistently described mathematically exists somewhere in this mathematical multiverse. This is the ultimate multiverse. Far beyond simple variations in physical constants, it includes fundamentally different mathematics. structures with different numbers of dimensions, different topologies, different causal structures, perhaps even different logic. Current observations don't seem extremely atypical, consistent with the hypothesis, though determining typicality is difficult. Another objection is that not all mathematical structures can exist physically. Some might be logically possible, but physically impossible. But the hypothesis claims mathematical and physical existence are identical. There's no separate physical existence beyond mathematical consistency. This dissolves the objection, but at cost of radically redefining existence. We usually think existence means more than mathematical possibility. Something can be mathematically describable without being real. Fictional universes in novels are describable but not physically real. The mathematical universe hypothesis erases this distinction. All describable structures exist with equal reality. This seems counterintuitive. Our universe feels more real than imagined alternatives. We experience only one reality, not all possibilities. But Tegmark argues this is selection effect. We experience one mathematical structure because we're part of it. Beings in other structures experience those. No structure is more real than others objectively. Each is real to inhabitants of that structure. The hypothesis also addresses Wigner's question. Mathematics describes reality perfectly because reality is mathematics. There's no mystery about mathematical effectiveness. We're discovering the mathematical structure we inhabit. If the hypothesis is correct, what lies beyond our universe is all of mathematics. Every theorem, every consistent axiom system, every geometric structure physically exists. Beyond lies infinite diversity of existence, including structures we can barely imagine, and structures beyond our imagination entirely. Some structures might be similar to ours with minor variations. Others might be radically alien, with completely different fundamental principles. The mathematics governing some structures might be incomprehensible to us. Our mathematical intuitions developed for our structure might not apply elsewhere. This raises questions about whether all structures are describable in principle. Are some structures beyond any mathematical description? If so, the hypothesis might not be complete. Beyond mathematical structures might lie something even more fundamental. But if mathematics is truly universal, capturing all logical possibility, then mathematical multiverse is complete. The hypothesis is deeply philosophical. It treats existence as a mathematical property rather than something added to mathematical description. Philosophers debate whether existence is a property at all. Kant argued existence is not a predicate. Adding "one" doesn't change what something is. If existence isn't a separate property, then mathematical consistency might be sufficient for existence, supporting Tegmark's view. The mathematical universe hypothesis thus provides maximally expansive answer to what lies beyond. Everything possible exists somewhere. Our universe is one point in an infinite space of possibilities. Beyond lies infinite diversity of mathematical reality. Whether this is satisfying or merely pushes questions further is matter of perspective. Why does mathematics exist? Why is there logical structure rather than nothing? These questions might be meaningless if mathematics is all there is. But they illustrate how even comprehensive answers raise new questions. Various religious and philosophical traditions have contemplated what lies beyond the universe, offering perspectives that complement scientific investigation. Ancient Greek philosophy distinguished between the cosmos, the ordered universe, and chaos, the disordered void beyond. Pythagoreans believed mathematics governed cosmos, with harmonious numerical relationships structuring reality. Plato proposed that beyond physical world lies realm of perfect forms, ideal templates that physical objects imperfectly instantiate. The realm of forms is more real than physical world, which is mere shadow or reflection of forms. What lies beyond physical universe in Platonism is eternal unchanging reality of pure forms and mathematical truth. Aristotle rejected separate realm of forms. For Aristotle, form and matter are aspects of single reality. But Aristotle posited an unmoved mover, a first cause that sets universe in motion without being moved itself. God is transcendent, outside universe, eternal, while universe is temporal. God created universe ex nihilo, from nothing. What lies beyond universe in these traditions is God, along with perhaps angels or other supernatural beings. Different theological interpretations vary in detail. Some emphasize God's transcendence, others God's immanence in creation. Pantheism identifies God with universe rather than placing God beyond. In pantheism, universe is God, eliminating the beyond. Panentheism holds that universe exists within God, but God exceeds universe. What lies beyond universe is more of God not contained in creation. Hindu cosmology describes infinite cycles of creation and destruction. Brahma creates, Vishnu preserves, Shiva destroys universes in eternal cycle. Beyond our universe lies previous and future universes in eternal sequence. Ultimate reality is Brahman, unchanging ground underlying all change. Buddhist philosophy emphasizes emptiness, shunyata. All phenomena lack independent existence, arising interdependently. What lies beyond universe might be emptiness, though this doesn't mean nothingness but rather the absence of inherent existence. Some Buddhist schools describe multiple world systems, numerous universes existing simultaneously. Beyond our universe are countless others. Taoism speaks of the Tao, the way or path underlying reality. The Tao is beyond description, beyond conceptualization. What lies beyond universe is the Tao, the source from which all things emerge and to which they return. Indigenous traditions often don't sharply distinguish universe from beyond. Reality is unified, interconnected, with spiritual and physical realms intertwined. What lies beyond visible world might be spirit realm or dream time, accessible through ritual or altered consciousness, but not separate from physical reality. Modern process philosophy, following Whitehead, sees reality as fundamentally process rather than substance. Universe is dynamic becoming, not static being. What lies beyond any given state of universe is its future becoming, the potential actualizing in creative advance. Existentialist philosophy focuses on human existence and meaning rather than cosmic structure. Questions about what lies beyond may be less important than how we live here. Existentialists might argue obsession with beyond distracts from engagement with present reality. The beyond is irrelevant if unknowable. These diverse traditions show humans have long contemplated what lies beyond immediate experience. The question is ancient and universal across cultures. Modern physics approaches the question with different tools, mathematics and observation rather than revelation or contemplation. But the philosophical questions physics encounters echo traditional concerns: existence versus non-existence, infinite versus finite, eternal versus temporal. Physics hasn't rendered traditional perspectives obsolete. It has added technical precision and empirical constraints, but hasn't eliminated mystery. Perhaps what lies beyond ultimately requires both scientific and philosophical or spiritual perspectives for fullest understanding. Science describes structure and mechanism. Philosophy and religion address meaning and value. Different questions require different frameworks. For understanding what physically lies beyond universe, science provides best tools. For understanding significance of beyond, other traditions contribute. A complete understanding might integrate insights from all perspectives, recognizing each illuminates different aspects of profound mystery. While what lies beyond the universe might seem purely theoretical, observations do constrain possibilities, helping distinguish plausible from implausible scenarios. Cosmic microwave background observations provide crucial constraints. The CMB's uniformity suggests large-scale homogeneity, extending beyond observable region. If universe beyond our horizon were dramatically different, We might expect to see asymmetries at observable boundary. None are observed. The CMB's power spectrum matches predictions from simple inflation models with nearly scale-invariant fluctuations. This suggests physics producing fluctuations was smooth and uniform, not varying wildly, supporting extrapolation beyond observability. Measurements of spatial curvature show universe is flat or very nearly flat, within about 1% observational precision. Flat geometry suggests either infinite extent or very large finite size with non-trivial topology. Small finite universes are ruled out. If universe has compact topology, we should see repeating patterns in CMB or galaxy distributions as light travels multiple times around. Searches for such patterns have found no convincing evidence, implying that if topology is compact, the repeat scale exceeds observable size significantly. Observations of supernovae and cosmic acceleration constrain dark energy properties. Dark energy appears consistent with cosmological constant, not evolving significantly. Constant dark energy implies eternal accelerated expansion, establishing event horizons and limiting future observability, but not directly telling us about beyond. Particle physics observations constrain fundamental constants: electron mass, fine structure constant, other parameters of measured values that appear constant. If different regions had different constants, we might expect gradients or discontinuities at boundaries. No evidence for variation exists within observable universe. This suggests constants are uniform at least across observable scales, supporting extrapolation that constants remain same beyond observation. But anthropic reasoning warns against overconfidence. We observe constants permitting observation. Beyond might have different constants with no observers to detect them. Gravitational wave observations beginning in 2015 provide new observational window on universe. So far, gravitational waves from black hole and neutron star mergers match general relativity predictions and show no anomalies suggesting physics beyond standard model. As gravitational wave astronomy develops, it might detect signals from early universe or exotic sources, potentially revealing information about beyond. Primordial gravitational waves from inflation, if detected, would confirm inflation occurred and provide details about physics at extremely high energies. This would strengthen confidence in eternal inflation and multiverse predictions that follow from inflation, indirectly supporting ideas about what lies beyond. Neutrino observations, particularly from supernovae and cosmic rays, test standard particle physics. No anomalies suggesting new physics or non-standard conditions have been found. This consistency across observations from different distances and directions supports uniformity of physics, suggesting similar physics beyond observation. Precision tests of general relativity across accessible scales show excellent agreement. No deviations suggesting modified gravity or higher dimensional effects have been detected. This constrains extra dimensions to be either very small or very weakly coupled, affecting string theory predictions about accessible structures beyond our universe. The absence of magnetic monopoles, cosmic strings, domain walls, and other topological defects predicted by some theories constrains phase transition history. If universe underwent certain symmetry-breaking transitions, defects would be produced. Their absence limits which transitions occurred or requires inflation diluted them. This constrains early universe physics, affecting predictions about multiverse structure and what might lie beyond. Fine-tuning observations, the apparent special values of constants permitting life, constrain explanations. Constants appear finely tuned a few percent or better. This supports either anthropic multiverse explanations or design hypotheses, though it doesn't definitively prove either. Without multiverse, fine-tuning seems remarkable and requiring explanation. Multiverse explanations require multiverse to exist, which is what observations can't directly verify. The anthropic constraint that we observe a universe permitting observation is strongest constraint, but also most obvious. It doesn't tell us what lies beyond, except that if beyond includes other universes, most don't permit observers like us. Taken together, observations support a relatively conservative picture. Universe is large or infinite, flat or nearly flat, homogeneous on large scales, governed by uniform physics. What lies beyond observable region is probably more of the same, not radically different structures or physics. But observations don't rule out multiverse scenarios where our universe is one bubble among many with varying properties. They also don't rule out finite but very large universe, perhaps many times observable size, with overall topology we haven't detected. Observations thus constrain possibilities without uniquely determining answers. They eliminate some ideas while leaving multiple plausible scenarios. Future observations will continue refining constraints. Better CMB measurements, larger galaxy surveys, gravitational wave detections, neutrino astronomy all provide new information. But fundamental limits exist. Regions beyond event horizon will never be observable regardless of technological advance. Within these limits, observations guide theorizing, keeping speculation tethered to empirical reality and preventing complete speculation. What we can say observationally is that universe is vast, uniform, and well described by general relativity and standard model physics across accessible scales. Extrapolating beyond, while uncertain, reasonably suggests continuation of similar structure and physics, though multiverse alternatives remain possible. A fundamental challenge for understanding what lies beyond the universe is that direct observation of beyond observable regions is impossible in principle. The observable universe has finite extent because light travels at finite speed and universe has finite age. Only regions from which light has reached us are observable. This creates a hard boundary called the particle horizon, at roughly 46 billion light-years in proper distance. Beyond. This horizon, light simply hasn't had time to reach us yet. No observation, regardless of instrument sensitivity, can penetrate beyond. As time passes, the particle horizon grows. Light from slightly farther regions reaches us, expanding observable universe. But dark energy complicates this. Accelerating expansion creates a vent horizon, beyond which regions recede so fast their light never reaches us. If multiverse exists with separate bubble universes, those bubbles are even more deeply unobservable. They're not just distant, but causally disconnected. No signal, light, or gravitational wave or any messenger can travel between separate bubble universes if inflating space separates them. The bubbles are separate universes in the stronger sense. No information transfer possible, no causal influence, no observation even in principle. This raises philosophical question about scientific status. If something is unobservable in principle, does claiming its existence constitute science? Traditional scientific methodology requires empirical testability. Hypotheses must make predictions checkable through observation. But modern physics routinely involves unobservable entities. Black hole interiors, quantum wave function, vacuum fluctuations all involve aspects not directly observable. The question is whether unobservable in practice differs importantly from unobservable in principle for scientific epistemology. Some philosophers argue the distinction matters. Practical limits might be overcome eventually. Principled limits cannot be. Others argue that indirect evidence suffices. If theory predicting unobservables explains many observations successfully, the unobservables gain credence. Atomic theory was accepted before atoms could be observed because atomic theory explained so much else. Similarly, multiverse theories might be accepted if theories predicting them explain observable universe features successfully. But critics maintain this stretches scientific method too far. Unobservable predictions that follow from theory aren't tested predictions but theoretical appendages. Real prediction means observable consequences that could disconfirm theory. Multiverse predictions typically can't be disconfirmed because they're unfalsifiable. This debate hasn't reached consensus. The scientific community remains divided on whether multiverse speculation is legitimate science or metaphysics. For our question of what lies beyond, impossibility of direct observation means answers must come from indirect reasoning. We infer what's beyond from extrapolating observed patterns, from theoretical consistency, from abductive inference to best explanation. These methods have merit but lack the definitive character of direct observation. They provide plausible answers, not certain knowledge. The impossibility also means we should maintain epistemic humility. Our confidence about beyond should be lower than about observable regions. Bold claims about what definitely lies beyond overreach available evidence. More tentative language is appropriate given fundamental observational limits. Some regions might become observable eventually as particle horizon grows, though event horizon limits this. But vast regions, possibly infinite, remain permanently beyond observation. This is not temporary ignorance but permanent structural limit. Accepting this limit is part of mature scientific understanding. Science has scope and boundaries. Not all questions can be answered empirically. The question what lies beyond might be partly answerable through inference, but not through direct observation. This doesn't make the question meaningless or uninteresting, but it does affect what kind of answers are possible and how confident we can be. These methodological questions matter as much as specific answers about what lies beyond. Process of inquiry must be reliable even when observation is unavailable. The impossibility of direct observation is thus both profound limitation and interesting challenge. Pushing science to develop new epistemological tools. Though other universes would be unobservable directly, some theories predict they might leave indirect signatures detectable in our observable universe. The most discussed potential signature involves bubble collisions in eternal inflation. If our bubble universe collided with another bubble during expansion, it might leave marks. The collision would affect space-time geometry in the collision region. This might create detectable patterns in the cosmic microwave background. Specific predictions depend on collision details, relative velocity, energy scales, when collision occurred relative to recombination. Several groups have searched CMB data for collision signatures. Some early claims of detection were made but didn't hold up to scrutiny. Most searchers find no convincing evidence for bubble collisions. Either they haven't occurred within observable region, or signatures are too subtle to detect. Future CMB observations with better sensitivity might detect signatures current observations miss. But null results so far don't provide positive evidence. Another potential signature involves quantum tunneling between vacua. If our vacuum state isn't absolutely stable, decay might be possible. Vacuum decay would create expanding bubble of different vacuum state. The bubble wall would move outward at nearly light speed. Some researchers propose that certain CMB anomalies might hint at non-standard cosmology, possibly connected to multiverse structure. The hemispherical power asymmetry, where CMB fluctuations differ slightly between hemispheres, might indicate special initial conditions or external influence. The cold spot, an unusually large underdense region, might be statistical fluke or might indicate void in matter distribution with unusual origin. These anomalies might be chance fluctuations in a fundamentally homogeneous universe, or they might hint at more complex structure. Their interpretation remains debated. They're not strong evidence for multiverse, but might provide hints if future observations strengthen patterns. Fine-tuning itself might be indirect signature. The apparent special values of physical constants might result from anthropic selection in multiverse. If multiverse explains fine-tuning anthropically, we should find ourselves in universe with typical life-permitting constants, not constants finely tuned beyond requirement. Testing this requires determining what counts as typical among life-permitting parameter space. This is difficult and results are disputed. Some analyses suggest our constants are roughly typical anthropically, Others find aspects that seem more finely tuned than anthropic reasoning predicts. String theory landscape might leave signatures if vacuum selection isn't random, but follows some dynamics favouring certain regions. If bubble formation preferentially occurs in certain landscape regions, statistical predictions about typical constants might be possible. These predictions could be tested against observations. Agreement would support landscape with that selection dynamics, but landscape structure is poorly understood. Making definite predictions requires solving string theory more completely than currently possible. Quantum branching in many worlds interpretation doesn't produce observable signatures. All branches occur, we experience one without seeing others. Some researchers have proposed interference effects between branches might be detectable, but these proposals are speculative and haven't led to practical tests. For most multiverse scenarios, absence of signatures is expected. Other universes are causally disconnected by design. The fact that we don't observe multiverse signatures doesn't prove multiverse doesn't exist, only that it's well hidden if present. This creates methodological difficulty. How do we test theories that predict unobservable entities leaving no observable traces? The answer might be that we test the theory's observable predictions while provisionally accepting unobservable implications if theory works well. Or we might conclude that permanently undetectable implications aren't properly scientific and should be regarded as metaphysical speculation. This debate continues. Meanwhile, searches for possible multiverse signatures continue, keeping open possibility of indirect detection. The absence of confirmed signatures so far suggests either multiverse doesn't exist, or it exists but leaves no marks, or signatures are too subtle for current observations. Future observations with better sensitivity will continue probing for signatures, though detecting them remains long shot given theoretical expectations. For now, we lack positive observational evidence for what lies beyond observable universe from indirect signatures. This leaves the question dependent on theoretical reasoning and extrapolation, rather than empirical confirmation, maintaining uncertainty about correct answer. While direct observation of what lies beyond is impossible, fundamental physics principles constrain possible answers, ruling out some scenarios. Conservation laws must hold. Energy, momentum, angular momentum and charge are conserved in isolated systems. If universe is quantum system, unitarity constrains possible interactions with beyond. Quantum information cannot be truly destroyed. Black hole information paradox involves similar issues. Does information falling into black hole get destroyed, violating unitarity, or preserved somehow? Resolutions propose information escapes through Hawking radiation, or is preserved in subtle correlations. Similar considerations might apply to cosmic boundaries. Causality requires causes to precede effects. Like cone structure of space-time enforces causal relationships. What lies beyond cannot causally affect us if outside our light cone. This constrains possible interactions with beyond observable regions. Within observable universe, causality holds. No faster than light signaling is observed. This suggests causal structure extends consistently beyond observation. Symmetry principles constrain physics. CPT symmetry, Lorentz invariance, gauge symmetries all restrict possible theories. If beyond obeys same symmetries, physics there must share certain properties with here. This reduces how different beyond can be. If beyond violates symmetries we observe, there must be boundary where symmetries change. Such boundaries might leave detectable signatures. Absence of symmetry, breaking signatures suggests either beyond shares our symmetries, or boundaries lie beyond observation. Locality principle states that physics at each point depends only on nearby points. No instantaneous action at distance. If beyond is spatially separated, locality prevents direct influence. Only through local interactions at boundaries could influence propagate. This drastically changes conception of beyond. Instead of more space outside, beyond is information surface containing our universe's description. Anthropic constraints limit possible physics in observable universe to ranges permitting observers. Beyond might have different physics, but we couldn't observe it. This doesn't constrain physics of beyond directly, but constrains our knowledge. We only observe anthropically selected region. Consistency with general relativity constrains cosmic structure. Space-time must satisfy Einstein's equations given matter content. This rules out certain geometries and topologies. Beyond must have geometry consistent with gravity and matter distribution. Standard model of particle physics has been tested extensively. Any beyond must explain why standard model works so well here. If fundamental physics varies beyond observation, there must be reason standard model emerges in our region. This constrains variation possibilities. Inflation success in explaining observations constrains early universe physics. Beyond must be consistent with inflation occurring in our region. This supports eternal inflation if inflation generically continues in some regions, but doesn't prove it definitively. String theory, if correct, constrains possible vacua through mathematical consistency. Only certain compactifications and configurations are allowed. This limits landscape of possibilities, though landscape remains vast. Beyond must lie within string theory's allowed structures if theory is correct. Loop quantum gravity and other alternative quantum gravity theories impose different constraints, affecting predictions about beyond. The correct quantum gravity theory, once established, will significantly constrain possible structures beyond classical cosmology. These constraints from fundamental physics narrow possibilities without determining unique answer. They rule out certain scenarios while leaving others viable. Working within constraints, theorists explore allowed possibilities, using mathematical consistency and physical principles to guide speculation. The constraints provide guardrails, preventing completely arbitrary speculation, keeping theorizing tethered to known physics. As understanding of fundamental physics improves, constraints will become tighter, further limiting what lies beyond could be. Eventually, complete theory of quantum gravity and fundamental forces might determine unique or highly constrained possibilities for beyond. But current knowledge leaves multiple scenarios consistent with constraints, maintaining uncertainty about correct answer. Though direct observation of beyond is impossible, future observations might provide indirect evidence, sharpening understanding of what lies beyond observable universe. Next-generation cosmic microwave background observations will measure polarization patterns with exquisite precision. Primordial gravitational waves from inflation would create specific polarization signature called B modes. Detecting this would confirm inflation occurred. Confirming inflation strengthens theoretical framework predicting eternal inflation and multiverses, indirectly supporting ideas about beyond. CMB observations will also better constrain spatial curvature. Precision below 0.1% might detect small curvature indicating finite universe. If curvature is detected, it constrains total universe size if topology is simple. This would tell us beyond observable region extends only so far before curving back. If no curvature is detected to high precision, it supports either infinite universe or very large finite universe, both implying vast beyond. Improved measurements of cosmological parameters will sharpen understanding of cosmic evolution and geometry. Supernova surveys and baryon acoustic oscillation measurements will continue mapping cosmic expansion history with improving precision. Understanding how expansion rate evolved constrains dark energy properties and total energy content, informing models of global structure. Large-scale structure surveys will map galaxy distributions across vast volumes, testing cosmological homogeneity at largest accessible scales. If homogeneity breaks down at larger scales, it would challenge standard cosmology and suggest different structure beyond observation. Continued null results for topology signatures will strengthen constraints on universe size if finite, pushing minimum size higher. Neutrino astronomy is developing. Large neutrino detectors might eventually detect cosmic neutrino background from early universe. Neutrinos decoupled earlier than photons. Cosmic neutrino background from 1 second after Big Bang would probe even earlier physics than CMB. Multi-messenger astronomy combining electromagnetic, gravitational wave, and neutrino observations will provide complementary information. Different messengers probe different physics. Combining them creates more complete picture of cosmic conditions. Particle physics experiments at higher energies might discover new particles or interactions relevant to early universe physics. Understanding physics at high energies informs inflation models and other early universe scenarios. Constraining predictions about beyond. Quantum gravity theories might make testable predictions as they mature. String theory, loop quantum gravity. Other approaches might predict observable signatures. Confirming predictions would establish correct quantum gravity framework, dramatically constraining possibilities for beyond observable structure. This incremental progress is how science typically advances when direct observation is impossible. We can't visit beyond, but we can become more confident about what it likely contains based on how our observable region behaves. The future of understanding beyond depends on continued patient observation, theoretical development, and careful inference from available evidence. Dramatic breakthroughs are possible but not guaranteed. Progress might be gradual accumulation of constraints rather than sudden revelation. Either way, future observations will contribute to answering what lies beyond, even if the answer remains incomplete. Understanding what lies beyond the universe requires accepting that some aspects of reality might remain permanently unknowable, a humbling limitation for human curiosity. Throughout history, humans have pushed boundaries of knowledge, seeking to understand everything. Science has been remarkably successful at revealing nature's secrets, but cosmic expansion and light speed create hard limits. Some regions are causally disconnected from us, making them fundamentally unobservable. This isn't temporary ignorance to be overcome with better technology. It's a permanent feature of universe's structure. Accepting permanent limits is difficult psychologically. We want to believe everything is eventually knowable if we try hard enough. But physics itself tells us this isn't so. There are things we can never know, not because we're insufficiently clever, but because reality has boundaries. These epistemological limits differ from practical limits. Practical limits might be overcome. Epistemological limits result from reality's structure. Some find this unsatisfying. If we can't know for sure, why pursue the question? Why not focus on answerable questions? Others find mystery appealing. The fact that some things remain unknown adds depth and wonder to reality. Complete knowledge might be boring. Mystery provides perpetual source of fascination and speculation. The limits of knowledge also provide humility. Science has explained vast amounts, but mysteries remain. This prevents arrogance. Recognizing what we don't and can't know is as important as recognizing what we do know. The cosmic horizon is a natural place for human inquiry to reach limits. It's where our observable region ends and unknowable begins. This creates poignant boundary. On one side, the known and knowable, studied and measured. On the other side, the mystery. Future generations will have same limits, perhaps pushed slightly farther as universe ages but not eliminated. Millions of years from now, if humans or descendants survive, they'll still face horizons beyond which lies unknowable. This suggests the beyond is not temporary gap in knowledge but permanent feature of existence from any finite perspective. Perhaps only an infinite observer could transcend all boundaries and know everything. But such observer would be equivalent to reality itself. From any limited perspective, inside reality, some of reality must remain beyond observation and knowledge. This is not failure, but simply the situation finite beings find themselves in. We're parts of reality, not separate observers viewing it from outside. As parts, we cannot observe the whole. We can only observe our local region and infer tentatively about rest. The limits of knowledge thus teach important lesson. Reality exceeds our grasp. What we know is subset of what exists. This should inspire both humility about current understanding and wonder at vastness of unknowable lying beyond our cosmic horizon. While unknowability might seem frustrating, there's profound beauty in recognizing that reality contains mysteries beyond our reach. Complete knowledge would mean no surprises, no discoveries remaining, no sense of wonder about hidden depths. This cosmic humility can be spiritually valuable, combating ego and self-importance with perspective on actual significance. Not knowing what lies beyond also leaves room for imagination. We can envision possibilities without being constrained by definite knowledge. Science fiction has long explored ideas about multiverse, parallel realities, higher dimensions. These remain imaginative possibilities because beyond is unknowable. If we definitively knew what lies beyond, imagination would be constrained. Not knowing allows creative speculation to flourish. Philosophically, the beyond raises profound questions about existence, reality, consciousness, meaning that resist easy answers. These questions wouldn't exist if reality were completely knowable. Mystery generates philosophical inquiry and reflection. The pursuit of knowledge about the unknowable might seem futile, but the pursuit itself has value, independent of reaching definite answers. Asking what lies beyond stretches our thinking, exercises our reasoning, deepens our understanding even if ultimate answers remain elusive. The journey matters as much as the destination. Exploring questions about beyond is valuable even without reaching final conclusions. Artistic expression often draws inspiration from mystery and the unknown. Vast unknowable cosmic reality inspires poetry, music, visual art. The beyond provides metaphor and symbol for human experiences of mystery, transcendence, connection to something greater. Art capturing sense of cosmic mystery resonates because it reflects genuine feature of reality, not just human imagination. Some find this diminishing. We're insignificant parts of incomprehensibly vast reality. Others find it liberating. Significance comes from within, not from cosmic importance. Meaning is what we create through our choices and values, not something granted by universe's structure. The beyond's unknowability thus doesn't threaten meaning but contextualizes it within properly humble understanding of our cosmic situation. Scientifically, the beyond motivates continued inquiry even without hope of definite answers. We keep probing limits, refining understanding of boundaries. This process yields genuine knowledge even if ultimate questions remain open. We learn about observable universe and about limits themselves. The beyond also inspires development of new methodologies. When observation fails, reasoning must substitute. This pushes philosophy and mathematics forward. Multiverse theories, anthropic reasoning, quantum cosmology all emerge from attempting to address what lies beyond observable. Even if answers remain uncertain, the intellectual tools developed have value for other problems. The beyond thus contributes to progress even without being directly knowable, spurring innovation in thought. Beauty in not knowing comes from recognizing that reality's depth exceeds human grasp while still allowing meaningful understanding within limits. We know much, we can't know all. This balance between knowledge and mystery seems optimal for finite minds in infinite reality. Complete knowledge might be overwhelming or boring. Complete ignorance would be frustrating and limiting. The middle position we occupy enables both understanding and wonder. The beyond represents the permanent mystery that makes existence interesting rather than routine, profound rather than mundane. Embracing this mystery rather than fighting it leads to richer engagement with reality as it is, not as we wish it were. The question of what lies beyond the universe connects deeply to questions about meaning and purpose, affecting how we understand our cosmic significance. If our universe is all that exists, bounded and finite, It might seem more comprehensible and our place within it more definable. But if beyond lies infinite expanse or multiverse of diverse universes, our significance might seem diluted in vastness. Does what lies beyond affect whether our lives have meaning? This question mixes cosmology with philosophy and values. From this perspective, what lies beyond doesn't threaten meaning because meaning never depended on cosmic importance. We create meaning through how we live, regardless of reality's total extent or structure. The anthropic principle connects to meaning questions. If multiverse contains vast diversity, we observe life-compatible universe because we must. Our existence is explained by selection effect, not by universe being designed for us, or our existence being cosmically important. This can seem to diminish significance. We're here by chance, not purpose. Universe wasn't made for us. But anthropic explanation is naturalistic, avoiding need for cosmic designer or purpose while explaining why we observe habitable universe. For those seeking meaning in natural framework, anthropic explanation is satisfying rather than threatening. Religious perspectives often find cosmic purpose in divine plan. God created universe and us for reasons, giving existence meaning. What lies beyond might be interpreted as part of divine creation. Other universes, if they exist, might serve divine purposes we don't understand. God's transcendence means beyond our universe is still within God's purview. No reality lies beyond divine concern. This maintains meaning within religious framework regardless of cosmological details. For non-religious perspectives seeking meaning, various options exist. Existentialists emphasize human freedom to create meaning through choices. What lies beyond is irrelevant because meaning comes from within, from how we choose to live and what we value. Humanists find meaning in human welfare, creativity, relationships, progress. These remain meaningful regardless of cosmic structure. Some find meaning in contributing to something larger than themselves, even if not cosmically large. Community, humanity, life generally. What lies beyond doesn't affect these sources of meaning because they're grounded in our actual situation, not cosmic totality. Transhumanists and cosmic futurists imagine humanity's long-term future, perhaps eventually spreading through galaxy or beyond. If our descendants or creations eventually explore vast regions, our current actions contribute to cosmic future, even if we're currently insignificant. But even these expansive visions are bounded by horizons. Most of reality will remain beyond reach. The pursuit of knowledge itself provides meaning for many. Understanding reality, including what we can know about beyond, is inherently valuable. This intellectual meaning doesn't require complete knowledge, only genuine understanding within our limits. Some philosophical traditions emphasize acceptance and peace with how things are rather than requiring cosmic importance for meaning. Buddhism's emphasis on letting go of attachment includes releasing attachment to cosmic significance, while finding meaning in present experience. Stoic philosophy similarly emphasizes accepting what we cannot change, while focusing on what we can control. What lies beyond is beyond our control. Focusing on it as source of meaning is misguided. Focus should be on what's accessible. These perspectives find what lies beyond interesting, but not determining for meaning and purpose. Practically, most people's meaning comes from immediate concerns: family, work, community, interests, relationships. Cosmological questions are fascinating but distant from daily meaning-making. What lies beyond doesn't affect these immediate sources of meaning. This suggests meaning is robust against cosmological details. Humans create meaning locally regardless of cosmic context. The question of meaning given what lies beyond might be confused category error, expecting cosmic structure to provide meaning when meaning comes from elsewhere. Understanding what lies beyond satisfies intellectual curiosity and expands understanding but doesn't determine whether life has meaning. Meaning is human concern requiring human answers based on values, choices, relationships, not cosmological answers based on universe's structure. Despite profound philosophical interest, what lies beyond the universe has virtually no practical implications for daily life or even for most scientific work. The beyond doesn't affect physics experiments, engineering projects, medical treatments, agricultural practices, or anything in technological civilization. Physical laws we use for practical purposes are tested locally. They work regardless of what lies beyond observable region. These intrinsic intellectual values justify investigation even without practical payoff. From perspective of funding priorities, lack of practical applications might seem problematic. Should resources go to questions without applications? But societies benefit from supporting pure research. Applications often emerge unexpectedly from curiosity-driven investigation. Quantum mechanics was pure theory before enabling modern electronics. General relativity was abstract before being essential for GPS. Supporting investigation of beyond might yield unexpected applications eventually. Though this isn't the primary justification. The primary justification is that humans are curious beings who value understanding. We want to know about reality regardless of applications. This desire for knowledge is part of what makes us human. Suppressing it would diminish humanity even if practically neutral. Cultures that support pure inquiry tend to be more creative and innovative generally. The attitude of curiosity transfers across domains. So supporting cosmological research about the beyond contributes to broader culture of inquiry benefiting practical domains indirectly. For individual scientists, work on beyond questions is professionally relevant even if practically irrelevant. Careers in cosmology involve studying these questions. Publications, grants, academic positions depend on contributing to understanding. This professional structure exists because societies value the knowledge produced, even without immediate applications. From educational perspective, teaching about the beyond develops critical thinking, quantitative reasoning, and scientific literacy. Students learning cosmology gain skills transferable to practical problems, even if cosmological knowledge itself isn't practically used. The beyond thus has educational value beyond its direct content, teaching how to think scientifically about difficult questions. Philosophically, thinking about beyond develops intellectual virtues, open-mindedness, logical reasoning, comfort with uncertainty, epistemic humility. Human civilization has always supported some pure inquiry alongside practical work. This balance seems healthy and enriching. The beyond represents extreme case of practically irrelevant but intellectually profound inquiry, valuable for what it reveals about reality and our place in it. Maintaining research into such questions demonstrates civilizational commitment to understanding beyond immediate survival and comfort. This commitment defines us as more than merely practical beings. We're creatures who wonder about existence itself regardless of practical implications. As we conclude our exploration of what lies beyond the universe, perhaps the most important lesson is learning to embrace the unknown rather than fear or fight it. Human psychology often treats uncertainty as an uncomfortable state to be resolved through acquiring information and reaching conclusions. But some uncertainties can't be resolved. They're permanent features of our epistemic situation, not temporary gaps to be filled. The beyond represents such permanent uncertainty. We can speculate, theorize, reason, but we cannot know definitively. Learning to be comfortable with this is important skill, applicable beyond cosmology to many life situations. Much of life involves uncertainty that can't be eliminated. Health outcomes, relationship futures, career trajectories all involve irreducible uncertainty. Accepting uncertainty without demanding false certainty or giving in to paralysis is crucial life skill. The cosmological beyond provides practice field for developing this acceptance in low-stakes intellectual context. If we can embrace uncertainty about cosmic structure, we can better embrace uncertainty in daily life. The beyond also teaches that not all questions need answers to be valuable. Questions can be worth asking even without definite answers. The process of inquiry, exploring possibilities, Testing reasoning has value independent of reaching conclusions. This process-oriented view of knowledge-seeking is psychologically healthier than demanding definite answers to every question. It allows engagement with profound questions without frustration when answers remain elusive. Intellectually, embracing unknown means remaining open to multiple possibilities rather than prematurely committing to one answer. Dogmatism claims certain knowledge where none exists. Intellectual humility acknowledges limits while continuing inquiry. The beyond exemplifies a situation where humility is appropriate. Multiple scenarios remain plausible. Overconfidence is inappropriate. This intellectual humility extends to related questions. How did the universe begin? Why does anything exist? What is consciousness? These profound questions might also resist definite answers. Embracing this possibility allows engagement without frustration. Philosophically, the beyond connects to acceptance of finitude. We're finite beings in vast reality. We cannot know everything. Science and wonder are not opposed. The most profound scientific understanding often evokes the deepest wonder. Understanding what we can know about the beyond while acknowledging what we cannot know embodies this synthesis of knowledge and wonder. The beyond exemplifies this situation. Complete answer might never come, but understanding deepens through continued work. For those seeking meaning and purpose, embracing unknown means finding meaning in present experience rather than requiring cosmic answers. Purpose comes from our choices and values, not from definitively understanding what lies beyond observable reality. This locates meaning appropriately in accessible human domain rather than distant cosmic questions. Spiritually, for those so inclined, the beyond can represent mystery that connects to divine mystery or transcendent reality. Not knowing what lies beyond can be experienced as openness to transcendence, rather than frustrating gap in knowledge. Different spiritual traditions offer frameworks for relating to cosmic mystery in ways that enrich rather than diminish experience. Culturally, embracing unknown means supporting inquiry into profound questions, even without guarantee of definite answers. Societies that value such inquiry are intellectually richer and demonstrate commitment to understanding beyond immediate practicality. The question itself, more than any specific answer, enriches human understanding and experience. As we reach the end of our exploration, we haven't definitively answered what lies beyond the universe. Multiple possibilities remain. But we've examined the question carefully, explored theoretical frameworks, considered observational constraints, and reflected on philosophical implications. We've learned that the question has multiple interpretations, each with different answers. We've seen how modern physics addresses these questions. Most importantly, we've learned to appreciate the question itself and to be comfortable with uncertainty about the answer. What lies beyond the universe? Perhaps more space, perhaps other universes, perhaps nothing, perhaps something we cannot imagine. The honest answer is, we don't know and might never know definitively, and that's okay. Thank you for journeying with me through this exploration of cosmic boundaries, this patient investigation of what might lie beyond the universe's edge. I hope you found peace in recognizing that some questions remain forever open, that mystery enhances rather than diminishes reality, and that not knowing can be as valuable as knowing. What lies beyond the edge of the universe? Multiple answers exist depending on what we mean by edge and by universe. Beyond the observable horizon lies more space. Beyond a finite universe might lie curvature, bringing space back on itself. Beyond our bubble might lie other universes in vast multiverse. Beyond the Big Bang might lie previous states or quantum timelessness. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released its need for certainty and definite answers. The mysteries we've explored perhaps help you feel both small in cosmic vastness and significant in your capacity to contemplate boundaries of existence itself. Sleep well tonight, knowing you inhabit a universe whose full extent remains unknown. where beyond observable reaches perhaps infinite diversity or infinite sameness, or simply more universe continuing forever. Beyond lies mystery that will remain mysterious, wonder that will remain wonderful, unknown that will remain unknown. Dream peacefully of edges that might not be edges, of boundaries that depend on perspective, of multiverse diversity or cosmic uniformity. Dream of questions without answers yet valuable for being asked. Dream of human curiosity reaching toward the unreachable and finding meaning in the reaching itself. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward an appreciation for mystery, comfort with uncertainty, and wonder at reality's depth that exceeds all understanding. What lies beyond the edge of the universe? We don't know. Perhaps we can't know. Perhaps the question itself is more valuable than any answer. Perhaps embracing the unknown is the wisest response to mysteries that resist resolution. Good night.